So this little tool is going to be a way for us to just experiment a little bit with different notions of addition and scalar multiplication. So we have here two vectors in purple and green that we can move around. And then we're showing in red here the sum of those two vectors. We can also slide these little things here to show us different scalar multiples of the vector. So this purple dot here is the relevant scalar multiple of the purple vector, and then the green dot is the relevant scalar multiple of the green vector. So we can play around with this a little bit. And what we can do is actually define addition and scalar multiplication differently by opening up these folders and playing around with these formulas. So if I wanted to match the activity that we're working on here, 2.1.2, I might want to define my addition operation as, well, I'm going to add the first two components. So that's what this f function is doing, x, y, z, w. The first component is x plus z. But then I want to multiply the y components. So instead of y plus w here, I want y times w. So that's going to be my new addition operation to make it match up with, so I changed this to y plus w instead of y times w instead of y plus w, to make it match up with this definition for how we add vectors with our new type of arithmetic. And then in the scalar multiplication section, when I multiply c times xy, I'm going to multiply the c times the x, but I'm going to take y and raise it to the cth power. So I'll just change that definition in there as well. And so now as I play around with these, I notice that as I sort of extend, as I scalar multiply my purple vector by different scalars by changing the c1, it looks like it's also just kind of stretching my vector in one direction or another. But interestingly, as I start to make c negative, what's happening?
We can't actually see what's happening.
You can't see what's happening because I forgot to switch my screen. I'm sorry about that. So as I play around with the scalar multiple of my first vector, I told you I'm discombobulated today. It looks like scalars that are bigger than 1 are also kind of stretching my purple vector. Scalars less than 1 are shrinking it. But as I start to make my scalars negative, it doesn't do what we would expect it to do, right? Ordinary scalar multiplication would give us something opposite, right, on the other side of the origin, but that's not happening here. Right? If I do that with my green vector, my vectors, ooh, that's interesting. So this one, it looks like as I scalar multiply my green vector by bigger and bigger scalars, that it's just sort of moving out horizontally instead of moving out vertically. And that's true even if I drag it to negative scalars. So this is a very different notion of scalar multiplication than the one that we're used to, right? Similarly with addition, notice that even this first example, right? Typically when I add two vectors, I expect to see their sum at the other vertex of a parallelogram that these two vectors make, right? And that's how ordinary vector addition works. And it looks like it almost happens in some cases, but it breaks down pretty quickly. Like let's say I take these two, right? Clearly this red sum is nowhere near at the edge of the parallelogram that would be formed by these two vectors. So clearly there is something very different about this kind of addition and scalar multiplication. Ooh, that's kind of interesting. So here's scalar multiples of that v. And so the question is, can we believe what we're seeing, right? Is this type of addition and this type of scalar multiplication actually a valid kind of algebraic structure that might have a chance of meeting these 8 properties that define for us what a vector space is? So the task in activity number 2, and I want to give you a chance to start working on this with your group. This is probably going to take, I'll give us 15 minutes or so to be working on part A for sure, and part B if you can get there, to show that this operation, so these operations of addition and scalar multiplication, satisfy the distributive property. So this number 8 condition here is met. And that it also contains an additive identity element. And to do that, you have to figure out what should the coordinates of this z vector be, so that if I add that z vector to any x1, y1, that the result is the same x1, y1 as we would have come out with in the first place.
Professor.
All right. So, nice work, first of all. What I see happening in your teams in this work is that you're doing a very effective job at discovering what goes on the sort of cocktail napkin version of the proofs that we're writing here. And so what I want to spend a few minutes looking through together is that process of transforming your cocktail napkin sketch into something that looks more like a formally written up proof. This is the habit that we want to start to inculcate this semester, because that habit is going to serve you very well as you get into the more upper level courses in the math major, where writing proofs is your sort of everyday responsibility. Excuse me. With the first part of this activity, we were supposed to show that this funny looking addition and funny looking multiplication satisfies two of the properties that go along with being a vector space: the distributive property of scalar multiplication over scalar addition, and then also the additive identity property. So let's talk about part B first, actually, because I think that proof is going to be a little bit shorter, and I think it's going to be a little bit easier for us to see the difference between the cocktail napkin version and the polished written version of this proof. So this is team number 2, who was looking for the coordinates of a z vector, so call it x comma y, such that every x1, y1 that we add to z is going to produce the sum, which is the same as the original x1, y1. And so on their cocktail napkin, they write that in the x term, when I add x1, y1 plus x comma y, the x term is going to be x1 plus x. And if we need that to be equal to x1, then x needs to be equal to 0, which I agree with. Similarly, in the y term, because in our funny multiplication operation, the y coordinates get, in our funny addition operation, the y coordinates get multiplied by one another. And so if the y coordinate needs to remain unchanged, we figure out that the y coordinate of our z, our additive identity element, should be 1, because 1 times anything is just equal to that thing. Right? And so the conclusion that comes out of your cocktail napkin, and the thing that you would sort of circle down at the bottom of your napkin, is z must equal 0, 1. That thing is going to be our additive identity. But this is a cocktail napkin. Like, if someone is just sort of looking at this, probably it's not going to make sense to them. Hopefully it still makes sense to you, having just done this work. But the goal, obviously, of writing a proof, as we talked about last time, is we need somebody to be able to pick this up and to understand it from start to finish without you looking over their shoulder and kind of pointing at the napkin and explaining what's happening at each one of those steps. So what I thought that I would kind of do with you for a minute is go back to our sort of 5-part proof scaffold, right? Introduce the thesis, set the context, assert the hypothesis, state the burden of proof, list all your implications, and then restate the conclusion. And look at how this cocktail napkin would appear in that proof format. So the introduce the thesis part of the work is just where we sort of state the claim that we're about to prove. I'm going to call it a claim. So the claim is that the set V contains an additive identity. Let's call it Z, which satisfies. And then we'll just sort of write out here, this is the equation that the additive identity is satisfy. X1, Y1, funny addition with Z needs to equal X1, Y1. By the way, one of the things that I wish our authors did a little bit differently, and I guess they do it here in this problem, is that they also give us a quantifier. So let me make a little space here because I need to add the rest of what they have written down there. They add the quantifier for all x1, y1. In B. Right, so here is the thesis. Here's the thing that we want to set about to try to prove, right? That there exists, maybe another way to say this, is that there exists in the set V an additive identity which satisfies blah, blah, blah. So anytime we're quantifying something using those identifiable catchphrases like there exists and for all are going to be really helpful when it comes time to go and write the proof. And so now in the set the context stage is when we begin our proof, which usually mathematician will write the word proof in boldface at the beginning of that line so that the reader knows, okay, now the argument is going to start, right? And to set the context, what we need to do is go back and look at any of the any of the statements and the assertions that were made and things that were kind of implicitly defined as part of the thesis above. And we'll want to sort of restate those things to bring them into existence as part of the proof. So what I'll say here is let V so maybe I'll say it this way. Let's let V as well as my funny addition, multiplication, let those things be defined as above. So they're written somewhere, above this activity, whatever. I don't want to retypeset them now because that's not the greatest use of our time. So let's let these things be defined as above. But the other things that we need to be able to assert is we need to be able to tell the reader something about x1, y1. Right? I shouldn't write x1, y1 as part of my proof until in the proof I introduce the reader to what x1, y1 are. Right? So because we have a universal quantifier on x1 and y1, the thing that we're about to write needs to be true no matter what x1 and y1 are chosen. Right? It needs to be true for all x1, y1 in the vector space. And so anytime we have a for all assertion, in the proof, that translates to an arbitrary choice. So a choice of x1, y1 that we don't get to make, but the universe is kind of making it for us. Some random fate is kind of selecting an x1, y1 for us. And so we'll call attention to that fact by saying, let x1, y1 in V be chosen arbitrarily. I'm just going to editorialize here. This means we don't choose it. We don't choose it, kind of the universe does, right? Maybe I'll say it this way. The proof needs to work for any such. Okay. So setting the context, we need to sort of say, what are V and my funny addition and funny multiplication? I'm just going to say they're defined as above. And then we'll also say, let's choose a V arbitrarily. So the proof that we write after this needs to work no matter what x1 and y1 are chosen right there. And then I think we're ready at that point to assert the hypothesis. And the hypothesis that's coming from the cocktail napkin. If I can sort of quickly switch back to the cocktail napkin, I'll switch back in a second. The cocktail napkin assertion is that z equals 0, 1, 0, 1 is going to be the desired additive identity. And so if that's our hypothesis, then this is our place to say so. So usually I'll use a verb like suppose. So suppose that z is 0, 1. And then stating the burden of proof means to tell the reader exactly what we're about to demonstrate to them. And so usually that comes in the form of a sentence that begins with we will show. So we will show that this element of V satisfies the additive identity property. So there's my hypothesis, there's my burden of proof. And now we get to list all the implications. So this ends up being often the sort of meat and potatoes part of where the proof is. This is where the nutrition resides in the proof. So now we basically have to take this cocktail napkin version and reconstruct it. Maybe I'll zoom in even further here just to make sure that we're all able to see what's on that napkin. All right. So on that napkin, we have this work that sort of led to the derivation of a z, 0, 1. And the work that we put in our proof is probably going to almost look like the reverse of what we wrote there. Because what we are trying to show is that for all x1, y1, so the for all is already taken care of by our definition of x1, y1 as being arbitrary, x1, y1, funny addition z needs to equal x1, y1. And so this statement here in gray, let me get back to my more legible screen. This statement here in gray is the one that we need to now prove is a true statement. And to do that, we just have to do a computation, right? We need to compute the left-hand side and show that that left-hand side is equal to that right-hand side. If we do that, then we've succeeded. So we'll just set out to do that calculation. x1, y1. Funny addition of z. And then we need to show that that's equal to something. Just give me a second to get my environment set up here. So in our manipulation, we want to start from the left-hand side of the desired equality that we're trying to prove and work our way towards the right-hand side through a series of equals. So this equals something, equals something, equals something, equals something, and eventually that something that we get should just be x1, y1. Right? What we don't want to do, for a variety of both historical and cultural reasons, is try to work on both sides of the equation at the same time and then sort of say, oh, look, they ended up being the same thing. For a lot of reasons that's not always the most convincing way to do it. So what this ends up looking like is we will remind ourselves of what that z definition is, x1, y1, funny addition, and z is 0, 1 now, right? And so here in the margin, we will remind our reader that this is by our construction of z. I might need to end up zooming out a little bit here so we can actually see everything. There we go. So notice what I'm doing. I have a grounds part of my argument, x1, y1, funny addition z, and I have a claim, x is that's equal to x1, y1, funny addition 0, 1, and then I have a warrant for that claim, right? The reason to believe that my claim follows from the evidence. And the reason for this claim to be true is that that's just definitionally what we decided that z meant, right? And so that's why I use the little catchphrase, by construction. So we decided that z was 0, 1, and that's why I can replace z by 0, 1 in this calculation. This is going to feel very sort of fussy and pedantic and legalistic. And we won't necessarily have to write this every time, but it's a very, very good habit to inculcate. Because if you're not sort of conscious of those things yourself as you're writing a proof, then you're much more prone to making errors in your proof along the way. So try to abbreviate as little as possible and skip steps as little as possible along the way. Okay, so then what would the next step be from here? x1, y1, funny addition 0, 1. What is this a good time to bring in? Like, what is useful information to help us get to the next step? Applying the funny definition of addition is going to be the next thing that I do, right? So my warrant is by definition of funny addition. And I'll do my funny calculation, right? x1 plus 0, comma, y1 times 1. Right? That is what the funny addition symbol is defined to do. Right? So there's my warrant by definition of funny addition. This is how I simplify that next line. Okay. And the next thing that I ought to do is try to simplify. Right? I have x1 plus 0. I know that I can simplify that just by properties of real number arithmetic. What is x1 plus 0? It's just x1. What is y1 times 1? It's just y1. And so what's my warrant there? Like, how do I know that the thing that I just wrote down is true?
Because they're just normal scalar numbers?
Yeah, these are just normal scalar multiplication and scalar addition of real numbers. So properties of the real numbers, let's say. Oops. So by properties of the real numbers, x1 plus 0 is equal to x1, y1 times 1 is equal to y1. And notice that x1, y1 is exactly the right-hand side that we were trying to get to in the first place, right? We're trying to substantiate this identity. And so we started with the left-hand side, x1, y1, funny addition z. And we were trying to show that that's equal to x1, y1. And we've just done it, right? By working from the left-hand side to the right-hand side. And so now is a good time to restate that conclusion. So what did we just prove? Thus, let's say it this way. Thus, because x1, y1 was arbitrary, we have that for all x1, y1 in the space V. That x1, y1 funny addition 0, 1 is equal to x1, y1 as desired. And we'll put in a little square to indicate that our proof is over, and then we'll go celebrate. So with all of my structure little blocks out of the way, the proof is only this long, right? It's still a pretty solid block of text though, right? And it's doing all of those different functions that we talked about last week, make a well-structured proof. It's setting the context by telling us what's going to be proven, and then introducing us to our main characters, v, funny plus, funny multiplication, x1 and y1 being chosen arbitrarily. I would also not include this little phrase here. And then our hypothesis, suppose that z is 0, 1, and our burden of proof, we're going to show that this element satisfies the additive identity property. Oh, and now that I'm rereading this, I realize that there's something else that we forgot to do. Does anybody see the step that I skipped here, like logically speaking? So one thing that I forgot to show, because it's part of the additive identity property, right? Whoops, I'm looking at the wrong thing. Zoom back here for a second. So the thing that we were proving, right, is the additive identity property. And it says that there exists some z where this thing is satisfied. But what they haven't actually said as part of this definition is that this z needs to be an element of my set, right? I can't have an additive identity element that doesn't live in the same set as all of the other vectors that we're working with. So I should probably have made that a part of my proof to actually verify that the z that I'm asserting is the additive identity actually is, honest to goodness, an element of this set of vectors. So let's add that little piece in, just for the sake of being as complete as possible with what we're writing here. So I'll just sort of wedge in another paragraph here and say that z belongs to v because. So we can see that z is an element of v since, and now is a place where we have to go back to the definition of what was the set v, because that's pretty important, right? So when I go back to the definition of what the set v was, the set v was the set of all points x, y, such that y is equal to e to the power x, right? So it's the set of all ordered pairs of real numbers where the second one is e raised to the first one. So I have to verify that my claimed element z actually meets that criterion. It's pretty quick to do, right? Maybe here's a good place to remind the reader of what the definition of v was. It's the set of all x, y such that y is equal to e to the power x. And we can see that z belongs to this set, since 1 is equal to e to the power 0. So this fills in a little missing link in what we had before. So I want to make sure that we get that property in there. Because it's entirely possible that we could have accidentally chosen an element which didn't belong to the vector space in the first place, it wouldn't be a vector space, sorry, it didn't belong to the set of elements in the first place. And so sometimes that happens, right? If we take just the positive natural numbers, 1, 2, 3, 4, 5, and so on, right? We could say, oh yeah, there's an additive identity, it's 0. Except that 0 didn't belong to that set in the first place, and so it wouldn't qualify, right? So that's why I had to add this little piece in here, and now we have a more or less complete proof. So to write up part A, here is Team 3's cocktail napkin. We're supposed to show that for any x1, y1, and x2, y2, for any x1, y1, and scalars a and b, that if I add my scalars and then do scalar multiplication, I get the same result as if I had done my scalar multiplications by a and b separately and then did my vector addition. And so here's the napkin version of what Team 3 has written for this one. So the left-hand side, a plus b, funny scalar multiplication, x1, y1. The right-hand side that we're supposed to get to is this big collection over here on the right, which is a, funny multiplication, x1, y1, funny addition with b, funny multiplication, x1, y1. So here's a case where if we're trying to use this work from one side of the equation to the other kind of philosophy, usually we like to start on whichever side of the equation has the more complicated expression on it, so that simplifying can be the name of the game. Because that's kind of a habit that we train our brains into as we're learning math up through the K-12 education. It's always try to make things simpler, try to make things simpler. And so we want to take advantage of that. So when I write the sort of list the implications part of this proof, I'm probably going to start with this right-hand expression and try to work it in to become something that looks like the left-hand side. All right, so let's try and turn this cocktail napkin into a more finished proof in the process. So what I'll do is start with these two introductory elements, right? Introduce the thesis. So what's my thesis? It's going to be the claim that for all x1, y1, and for all x1, y1 in my vector space, and a and b, which are real numbers, so scalars, right? We have, and then the equation that describes this property that we're supposed to satisfy. So that's this distributive property equation, which I'll quickly put into the camera one more time. A plus b times x1, y1 is equal to a times x1, y1 plus b times x1, y1. A plus b times x1, y1 equals a times, x1, y1. Funny addition with b, x1, y1. Okay, there we go. So that's the thing that we're supposed to prove. We've introduced our thesis, so now let's set the context. This is where we begin the proof. So notice we have a key phrase. We have a for all here. So how should I start my proof? What should I do to try to set this context? So let's let x1, y1 be any element in V. In other words, arbitrary. Right? I'm not going to leave that word in there, but that is what we mean there. x1, y1. So let's let x1, y1, and v be an arbitrary element. We also have a for all a and b scalars. So we have to introduce the reader to those. Whoops. A and b in real numbers. Be two arbitrary scalars. So now we've set a context. We know at this point in the proof what x1, y1 are, what a and b are, which means that now we can write equations if we want to. But we're not going to do that yet because we haven't asserted the hypothesis and we haven't stated the burden of proof. So that's what we'll do next. We will show that x1, y1, and a and b satisfy the distributive property. Listed above. Right, rather than re-type out. Well, I suppose the nice thing about having it all digital is I could just copy this equation down here. So we'll show that x1, y1, and ab satisfy the distributive property. Right, so we have to establish that this identity is true. So now we get to list our implications. So I'll just sort of start my sentence. By the way, notice that everything I'm writing in these proofs is actually a complete sentence. Even if it has mathematical notation and stuff kind of midstream, that grammatically speaking, everything has subjects and objects and a beginning and an end and punctuation and capitalization and correct spelling and all of that wonderful stuff. So it's not unlike any other kind of essay that we would write. So I wouldn't start a paragraph with an equation. I would start a paragraph by saying, we compute, and then write what it is that I'm computing as the direct object of that sentence. So as I mentioned before, starting on the more complicated side is probably the way to go. So I'll start on that right-hand side and say, I'm going to copy-paste it out of what I wrote here previously just to save some time. So here's my right-hand side. And so what should be the first thing that we do here? Like, what is a good first thing to apply? What would be my first warrant that I might bring to bear on simplifying this expression?
The scalar operation?
Yeah, the scalar multiplication. So by definition of my funny multiplication. Because in the order of operations, that's kind of the first thing that's happening inside of the parentheses here. And so I'll use that funny multiplication to replace a funny multiplication x1, y1 with, what would it be, a plus x1, or no, sorry, a times x1, comma, y1 to the power a. Right, so that's by definition of funny multiplication. And then I have my funny addition sign, and then I have the multiplication of b by x1, y1. So bx1, comma, y1 to the power b. Right, so that's a pretty long line. I'm just going to zoom out real quickly so we can see the full warrant that's there by definition of that funny multiplication. Can we still read the text at this scale, by the way? All right. So now what would be the next thing that we would probably want to simplify? Oops.
We should actually do the addition now.
Let's actually do the funny addition. So my warrant for the next step is going to be by definition of the funny addition, O plus. Yeah, so by definition of my funny addition, we'll do the addition. And when we add, we straight up add the first components, so ax1 plus bx1. And we multiply the second components, y1 to the power a times y1 to the power b. There we go. So that's how we use the definition of funny addition to go on to the next step. All right, so now what should we do? We're trying to still kind of begin with the end in mind, where we started on this complicated right-hand side. We're trying to make it to the left-hand side, which is a little bit more elegant. So here's where it's probably a good place to go back to your cocktail napkin for a second and see how is it that we can get back to that left-hand side that we're trying to get to. So that left-hand side that we're trying to get to on the napkin that this team drew here is a plus b, funny multiplication, x1, y1. And when they do that operation out, this is what they see. A plus b times x1, and then y1 to the power a plus b. And so we're going to end up following this arrow that they drew backwards to get us back to the original left-hand side that we started with. And in order to get there, I need to go just one more step in this multiplication by using ordinary properties of real number arithmetic. Right, so just like in our last step in our previous proof, our last warrant, excuse me, is going to be by properties of real number arithmetic. Excuse me. And according to the properties of real number arithmetic, I can factor out the x1 from the multiplication by a plus b, and I can use properties of exponents to replace y1 to the a times y1 to the b with y1 to the power a plus b, right? Using the properties of ordinary real number arithmetic, which impute to the algebra that we learned coming up through high school. And now that we're here, this is the place where we follow the arrow backwards on this cocktail napkin, right? We have now this lower left-hand piece. We just have to replace it with the upper left-hand piece. And to do that, we'll just use, well, we'll just make that replacement because we know that that's equal, but then we'll talk about what the warrant ought to be for that step. So this is a plus b, funny multiplication, x1, y1. But what's the warrant? What am I actually using there to make that last piece of the conclusion? Sorry. Zoom back in when I see. To get to this last step, what are we actually invoking there?
The funny multiplication?
Yes, the funny multiplication. Exactly. It's the definition of our multiplication operation. And that is exactly the other side of the equation that we were trying to establish. And so, actually, punctuation-wise, I'll probably put a period at the end of that sentence. It's going to look a little funny next to our funny multiplication symbol, but it's a complete sentence, right? So we did our computation, and now all we have to do is restate the conclusion. Therefore, for all x1, y1 in V and a and b real numbers, we have shown that, and I'll just copy this equation down again. And I suppose we'll say the word thus. Thus V satisfies the distributive property of scalar addition over scalar multiplication. Put in a black square or whatever is your favorite end of proof symbol, and then we can be done.